The room is dark. Somewhere a clock is ticking, but it is not the kind of clock you hear. It is an atomic fountain clock, counting the oscillations of cesium atoms, and it does not tick at all in any way a human ear could detect. It simply measures with an accuracy that would lose less than 1 second in 100 million years. And on the 29th of June, 2022, this clock and dozens of others like it around the world recorded something that should not have happened. The Earth finished its rotation 1.59 milliseconds early. 1.59 milliseconds, less than 1,000th of a second, fast enough that the day was the shortest ever measured since atomic timekeeping began in the 1960s. Fast enough that the previous record, set on the 19th of July 2020, was broken by a margin that made metrologists stop and stare at their screens. But the number itself is not what matters. What matters is the direction. For billions of years, the Earth has been slowing down. Every century, the day grows longer by about 1.7 milliseconds, as the moon's gravity tugs on the oceans and the tides, and slowly, inexorably, breaks the planet's spin. This has been one of the few certainties in a universe that offers very few. And now, in the span of a few years, the Earth has begun to speed up instead. It is not supposed to do that, and because it is doing that, we are now facing something that has never happened in the history of human timekeeping. For the first time, we may have to subtract a second from the global clock, a negative leap second, a minute with only 59 seconds in it, and the systems that run the world were never designed to handle that. Hello, and welcome to Sidereal. This is a video about time. Not time as a philosophical idea, not time as a feeling, but time as a physical thing, something that can be measured, something that can bend under the weight of a planet, something that can slow to a stop at the edge of a black hole, and something that, it turns out, is not behaving the way we thought it did. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps the channel. And I'm curious where you are listening from tonight and at what hour. Leave it in the comments if you feel like it. By the end of this, one question will have been turned over from every side, slowly, the way you turn a stone in your hand in the dark. The question is whether time is a constant at all, whether it ever was, and we begin with the day the planet broke its own clock. The Earth as a physical object is not a perfect timekeeper. It never has been. If you could stand outside the system and watch it spin, you would see a planet that wobbles, that shudders, that stretches and contracts, that speeds up and slows down in ways that are too small for a human to feel, but large enough for an atomic clock to measure with excruciating precision. The length of a day, measured from one solar noon to the next, is not a fixed quantity. It varies by microseconds from one day to the next, by milliseconds across seasons, by whole seconds across centuries. The moon pulls on the oceans and the tidal bulges act as a brake. Earthquakes shift mass and change the planet's moment of inertia. Winds push against mountain ranges. The liquid outer core sloshes and swirls and exchanges angular momentum with the solid mantle above it. All of these forces conspire to make the Earth's rotation irregular, and for most of human history, this irregularity was invisible to us. It was invisible because our clocks were worse than the planet. For thousands of years, time was measured by things that flowed or fell, the shadow creeping across a sundial, water draining from one vessel into another, sand running through a glass, a candle burning down. All of these were rough, and all of them, in the end, were calibrated against the sky, against the rising and setting of the sun and the slow precession of the stars. The Earth was not just one clock among many, it was the master clock, the standard everything else was set by. The first real improvement came in 1656, when the Dutch scientist Christian Huygens built a clock regulated by a swinging pendulum, drawing on Galileo's discovery that a pendulum of a given length always takes the same time to complete its swing. Overnight, timekeeping leapt from an error of minutes a day to an error of seconds. For the first time, a machine could begin to keep pace with the heavens. The pressure to do better came from the sea. A ship far from land could find its latitude easily enough from the height of the sun, but its longitude, its position east or west, depended on knowing, precisely, what time it was back at its home port. Every 4 seconds of error in that comparison meant a mile of error in position, and a mile of error off a rocky coast in the dark meant wrecked ships and drowned crews. The problem was so severe that in 1714, the British government offered an enormous prize for a solution. It was eventually won, after decades of obsessive work, by a self-taught Yorkshire carpenter named John Harrison, who built a series of sea clocks culminating in a marine timekeeper, accurate enough to carry the time of one place faithfully across an entire ocean. Time, for the first time, had become portable. You could take a moment from one part of the world and carry it intact to another. It is a strange thing to realize that for most of history, this was impossible, that the present in one place could not be reliably compared to the present in another. We first noticed the planet's own unsteadiness in the 1930s, when quartz clocks became precise enough to detect discrepancies between the time kept by the stars and the time kept by our machines. By the 1950s, the invention of the atomic clock made the discrepancies impossible to ignore. The first one, accurate enough to serve as a standard, was built by Louis Essen at the National Physical Laboratory in England in 1955, and it did something no clock before it had ever done. It ignored the sky entirely. An atomic clock does not care where the sun is. It counts the hyperfine transitions of cesium 133.9 billion, 192 million, 631,770 oscillations per second, and it does so with a fidelity that makes the Earth look like a broken pocket watch. In 1967, the General Conference on Weights and Measures redefined the second itself, anchoring it not to the turning of the planet, but to that count of oscillations in the cesium atom. The second became an absolute, and the Earth, the thing that had defined time for every human being who ever lived, became the thing that was wrong. This created a problem with no clean solution. We now had two kinds of time. One was atomic time, steady and perfect, kept by laboratories around the world. The other was astronomical time, the time of the spinning planet, the time that decides when the sun rises and when it sets, the time that human bodies and human agriculture and human civilization had been shaped by for 10,000 years. The two drift apart, because the Earth slows down while the atomic clocks do not. By the late 1960s, the difference was already approaching 10 seconds. 10 seconds is nothing in a human life. It is an eternity in navigation, in astronomy, in any system that needs to know exactly where the Earth is pointing at a given instant. So, in 1972, the keepers of the world's time reached a compromise. Whenever the gap between atomic time and astronomical time grew close to 9/10 of a second, they would add 1 second to the civil clock. The clocks would read 23 hours, 59 minutes, 59 seconds, and then, instead of rolling over to zero, they would read 23 hours, 59 minutes, 60 seconds, and only then, zero. A minute with 61 seconds in it, a pause, a breath, a small accommodation to the fact that the planet is not a machine. 27 times since 1972, that second has been added. Each time, the planet's irregularity was absorbed without most people ever knowing it had happened. The leap second became part of the hidden machinery of the modern world, like the satellites overhead or the cables on the ocean floor. And for 50 years it worked, in its awkward way, because the Earth always erred in the same direction. It was always running slow. We were always adding. Then, around 2016, the planet stopped cooperating. The service that monitors the Earth's spin publishes its measurements as a quiet stream of numbers, the difference between the time the planet keeps and the time the atoms keep. For decades, that difference had been growing in one direction, the planet steadily falling behind. Around 2016, the slope began to flatten. Then it reversed. The Earth was no longer losing time against the atomic clocks. It was gaining it. By 2020, the planet had recorded its shortest day in half a century. 2 years later, it broke that record again, on that day in June, by a margin that in the language of modern geodesy is not a margin at all, but a chasm. It is worth knowing how a thing as fleeting as a missing millisecond is even caught. The planet's rotation is watched, day and night, by a network of radio telescopes scattered across the globe, all of them staring at the same handful of quasars, brilliant, unfathomably distant beacons at the cores of far-off galaxies, so remote that for our purposes they hold perfectly still against the sky, fixed reference points pinned to the background of the universe. By recording the faint signal from a single quasar at several telescopes at once and comparing, to the billionth of a second, the slightly different moments at which the same wavefront arrives at each dish, astronomers can fix the exact orientation of the Earth in space. Lay one day's orientation against the next, against the flawless beat of the atomic clocks, and the length of that day falls out to a precision of microseconds. The short day in June was not inferred from a wobble or a model. It was measured, directly, against the most distant objects we can see, by an instrument the size of the whole planet. The Earth was timed against the universe, and the Earth came in early. And that reversal pointed at something no one had ever needed before. Not another second added, but a second taken away. A negative leap second, so the planet was speeding up. That was the measurement, clean and undeniable. The harder question, the one that would take years to even begin to answer, was why. To understand why the Earth had started hurrying, you have to look down, not at the floor, but through it, through the crust, through the mantle, through the 2,900 kilometers of slowly convecting rock that separate us from the core. The Earth is not a solid ball. It is a set of nested shells, each turning at its own rate, coupled to its neighbors by friction and magnetism, and the constant exchange of angular momentum. At the center is the inner core, a sphere of iron and nickel roughly the size of Pluto, solid, despite temperatures comparable to the surface of the Sun, held that way by the crushing pressure above it. Around it flows the outer core, an ocean of liquid metal whose currents generate the planet's magnetic field. Above that sits the mantle, solid rock that nonetheless creeps and deforms over geological time, carrying the continents on its back. And on the outside, the thin skin of crust and ocean and air, where everything we have ever known has happened. These shells do not all turn together. The inner core rotates at a slightly different rate from the mantle above it, sometimes faster, sometimes slower, too, and in recent years there is evidence that its rotation relative to the surface has slowed and may even have reversed direction, a finding published by researchers at Peking University in 2023, drawn from decades of earthquake waves that pass through the core and arrive subtly changed. The outer core flows in patterns that shift on timescales of decades, and when those patterns change, they can grip the mantle through the magnetic field lines that thread both layers and tug it, very slightly, faster or slower. Richard Gross, a geophysicist who spent his career at the Jet Propulsion Laboratory modelling exactly this, showed that a change in the flow of molten iron thousands of kilometres down can spin up the entire surface of the planet by an amount our instruments can read. A swirl in the deep, and the day grows shorter. But the core is not the only thing moving. The surface is changing too, and faster than the core, and in a way that is easier to see. The Greenland ice sheet is shedding mass at a rate of roughly 270 billion tons every year. Antarctica is losing well over 100 billion tons more. Ice that sat for millennia near the poles, close to the planet's axis, is melting and flowing toward the equator as water, spreading the planet's mass outward from its spin axis. The effect is the same one a figure skater feels. Arms drawn in, the spin quickens. Arms flung out, it slows. As meltwater moves toward the equator, it pushes mass outward, which by itself should slow the Earth down. The fact that the planet is speeding up anyway, against that drag, tells you how strong the other forces must be. And there is a darker irony folded into it. A study published in 2024 found that the redistribution of water from melting ice has grown large enough to measurably affect the length of the day on its own. We have warmed the planet enough to change how fast it turns. The clock and the climate are now linked. The shifting of mass can also happen all at once, violently. A great earthquake does not only shake the ground, it rearranges the planet's mass, and in doing so it changes the length of the day. When the enormous earthquake struck off the coast of Sumatra on the 26th of December, 2004, the one that loosed the Indian Ocean tsunami, it shifted enough rock toward the Earth's axis to shorten the day by nearly 3 millionths of a second, and to nudge the position of the North Pole by a couple of centimeters. The same thing happened again with the earthquake off Japan in March 2011, which shortened the day by around 1.5 millionths of a second, and shifted the planet's axis by perhaps 17 centimeters. These are tiny numbers, but they are real, and they are permanent, and they are a reminder that the spin of the Earth keeps a running account of everything that moves upon it and within it. Even the seasons leave their mark. As the great wind systems of the planet strengthen and weaken through the year, the atmosphere trades angular momentum with the solid Earth beneath it, and the length of the day swings back and forth by about a millisecond across the seasons, the planet spinning fractionally faster when the winds slacken, fractionally slower when they pick up. The Earth and its air are a single coupled system, passing momentum back and forth like two skaters holding hands. There is one more piece, and it is the strangest. The Earth does not spin around a perfectly fixed axis. The pole itself moves, tracing a small circle over a period of about 433 days. This is the Chandler Wobble, named for Seth Carlo Chandler, who detected it in 1891. The pole wanders by only a few meters, but because it shifts the distribution of mass relative to the spin axis, it feeds into the length of the day. For more than a century, the wobble was one of the most dependable features of the planet's motion, and then, recently, it changed. Its amplitude shrank. Its phase slipped in ways geophysicists do not fully understand. Some suspect the wobble is connected to the planet's sudden acceleration. Others think the influence runs the other way. The honest answer, the one written in the careful language of the journals, is that we do not yet know. To feel how unusual the present moment is, it helps to pull the lens back, far back, past human history altogether. The day has not always been 24 hours long. The same tidal breaking that is slowing the Earth now has been at work for billions of years, and it leaves a record. Certain ancient corals laid down fine growth bands, one for each day and a thicker pattern for each year. And when you count the daily bands in a fossil coral from the Devonian period, around 400 million years ago, you find not 365 of them in a year, but closer to 400. The year was the same length the Earth's orbit has barely changed, but the days were shorter, only about 22 hours each, because the planet was spinning faster. Go further back still, to well over 1 billion years ago, and the evidence written in layered sediments suggests the day was perhaps 18 or 19 hours long. The Earth has been winding down, slowly, for its entire existence. And the cause of that winding down is sitting in the sky every night. The moon raises tides in the Earth's oceans, and the friction of those tides drags very slightly against the planet's spin, bleeding off its rotational energy. By the iron logic of conservation, that energy has to go somewhere, and where it goes is into the moon's orbit. The moon is moving away from us, receding by about 3.5 centimeters a year, a number we know with extraordinary precision because the astronauts of the Apollo missions left mirrored reflectors on the lunar surface, and for more than half a century we have been bouncing laser pulses off them and timing the return. Every year the round trip takes a fraction longer. The moon climbs away, the day grows longer, and the two are bound together by the same slow exchange. Against that ancient, patient, billion-year slowdown, the planet's sudden recent decision to speed up is not a small wobble. It is a reversal of one of the deepest trends in Earth's history, and we cannot fully explain it. What we do know is harder to sit with than any single cause. The Earth's rotation is no longer predictable the way it was a generation ago. The models that forecast the length of the day, the models that tell the timekeepers when a correction will be needed, have lost their reliability. The planet has entered a regime where the interplay of core and ice and ocean and atmosphere produces results that surprise the people who study them for a living. We are, in a plain and literal sense, losing track of the ground under our feet, and the timing of that could hardly be worse, because the moment the planet became unpredictable is the moment our civilization became utterly dependent on time being exactly the opposite. The internet, the banks, the power grid, the satellites that tell your phone where it is, all of them run on time, signals that have to be smooth, continuous, and known in advance. The planet has chosen, after billions of years of slowing down, to start behaving erratically at the precise point in history when we can least afford it. And the first place that contradiction is going to break something is in a single second that we may soon have to remove. To understand why a single subtracted second is so dangerous, you have to understand that computers do not experience time the way you do. You feel time as a smooth flow, one moment sliding into the next without seam or edge. A computer experiences time as a count, a number that increases once per second, or once per millisecond, or once per billionth of a second. and that the entire machine trusts to only ever go up, smoothly, one step at a time, forever. A positive leap second bends that trust but does not break it. When a second is added, the counter is told to wait. At 23 hours, 59 minutes, 59 seconds, the clock holds for one extra tick, the 60th second, before moving on to 0. The sequence runs 58, 59, 60, 0. There is an unfamiliar number in the middle of it, but the count never goes backward and never skips. It is strange, but it is survivable. A negative leap second is a different kind of thing. To remove a second, the clock must jump from 58 straight to 0. The 59th second does not happen. The sequence runs 58, then 0, and in the gap between them is a number that was supposed to exist and does not. For a machine built on the assumption that every minute contains 60 seconds, that missing number is not a pause, it is a contradiction. A transaction that should have been stamped in the vanished second has nowhere to live. A navigation calculation that depends on the unbroken march of satellite clock offsets meets a discontinuity that runs the wrong way. A database that uses the timestamp as a unique key finds a hole in its own sequence. None of these are theoretical. They are the precise kind of fault that pushes distributed systems out of sync, that leaves financial ledgers disagreeing with one another, that makes an aircraft's navigation quietly lose confidence in where it is. We know this because the positive leap seconds already caused damage, and those were the ones we had practiced for. On the 30th of June 2012, a leap second was added, and parts of the internet simply fell over. A flaw in the way a widely used operating system handled the extra second sent affected machines into a loop, pinning their processors and taking the services running on them offline. Reddit went down. Mozilla had problems. The booking system of an Australian airline stumbled, and flights were delayed while staff fell back to checking passengers in by hand. 3 years later, on the 30th of June 2015, the protocol that keeps the clocks of millions of servers in agreement passed the leap second downstream unevenly. Some clocks took the extra second, some did not, and the disagreements rippled outward. Major cloud platforms saw spikes in delay. Systems logged timestamps that appeared, briefly, to run backward. The problems were patched within hours, but the lesson was unmistakable. The assumption of smooth, unbroken time is poured so deeply into the foundations of the digital world that even one extra second can crack it. And that was for the kind of leap second engineers had handled 26 times before. A negative leap second has never been handled. Not once. The protocols for it exist on paper. But paper is not a planet's worth of machines running code written by thousands of people over half a century. Much of it never once tested against a 59-second minute. The engineers who maintain the world's timekeeping software have discussed the negative leap second for years. And the discussions carry a particular tone, measured, careful, and uneasy. They know that somewhere in that vast inheritance of code, there is a line that will fail when the count goes the wrong way. They do not know where it is. They will not know until it fails. Faced with this, some of the largest companies in the world quietly stopped waiting for permission and built their own way around the problem. Rather than insert or remove a whole second all at once, they smear it, spreading the adjustment across many hours, slowing or speeding their clocks by a fraction so small that no single moment ever contains a discontinuity. By the time the day is over, the second has been absorbed, and not one timestamp ever had to confront a 60th second or a missing 59th. It is an elegant solution. It is also, in its way, a quiet declaration of independence. The companies that run much of the internet decided they would rather manage time themselves than trust the seam the official clock was handing them. Other systems sidestepped the problem in a more drastic way by refusing to follow the planet at all. Underneath the civil time we all use sits a purer timescale called International Atomic Time, which is nothing but the steady, unbroken count of the world's atomic clocks, with no leap seconds ever added. Civil time is just that atomic count with the leap seconds folded back in to keep it roughly aligned with the sky, and over the decades those accumulated corrections have pushed the two more than half a minute apart. The satellite navigation system goes further still. Its own internal time, set running in 1980, has never taken a single leap second, so it has drifted steadily ahead of civil time, second by second, and now leads it by a margin that the system simply carries in its software, and corrects for when it talks to the outside world. In other words, the machines that most need time to be smooth have quietly built their own private timescales that never flinch. And they let civil time, the time on your wall, do the awkward work of staying in step with a planet that will not cooperate. The leap second is the seam where those two philosophies meet, and it is the seam that is now being cut. The decision to face the deeper problem head-on was not made lightly, and it was not made quickly. For more than 2 decades, the international timekeeping community had argued about a more radical option than smearing. Abolish the leap second entirely. Let atomic time and astronomical time drift apart and never reconcile them again. The argument in favour was practical and cold. The leap second is a relic of an age when the position of the sun governed daily life. In the modern world, the time that actually matters is atomic time, the time of satellite navigation, of financial markets settling in microseconds, of networks that span the planet. If I really once said of Seta, astronomical time, the time of sundials and solstices, is a cultural inheritance, not a technical necessity. And the cost of keeping the link, the abolitionists argued, was a permanent, low-level risk of breaking the very infrastructure that civilization now runs on, all to honour a connection most people never think about. The argument against was harder to put into a budget, but its defenders felt it just as strongly. For all of human history, time was the sky, the day was the sun, the month was the moon, the year was the slow wheel of the stars. To cut the leap second was to sever the last thread tying the time on our wrists to the turning of the planet beneath us. It was to declare, formally, that the Earth was no longer humanity's clock. The drift, left uncorrected, is about 1 minute every century. In 1,000 years, solar noon would arrive an hour late. Eventually, far enough downstream, the sun would rise in what the clocks insisted was the middle of the night, and a civilization that had not chosen to recalibrate would live entirely out of step with the sky that made it. To one camp, that was a trivial price spread across an unimaginable span. To the other, it was the final disconnection, a small civilizational forgetting. For years the two arguments balanced, and so nothing changed, because the cost of changing the system seemed larger than the cost of leaving it alone. The question had been on the table for a long time. The body responsible had first taken up a formal proposal to drop the leap second back in the early 2000s, and it had gone nowhere, debated, deferred, sent back for study, deferred again. A decision expected in 2012 was postponed once more, the delegates unable to reach the consensus that their rules required. Nation after nation lined up on one side or the other, and the disagreement was not only technical but cultural, even faintly emotional. Some countries were reluctant to sever the ancient tie between the clock and the Sunday. Others were impatient with what they saw as sentimentality standing in the way of a system the modern world plainly needed. For 2 decades the matter sat unresolved, the leap seconds continuing to be inserted one at a time, while the larger argument went in circles. Then the planet started speeding up, and the balance broke. The prospect of a negative leap second, an event tested against exactly 0 real-world systems, tipped the scale. In November 2022, at a conference in Geneva, the member states of the International Telecommunication Union voted to abolish the leap second by the year 2035. After that date, coordinated universal time will no longer be adjusted to follow the rotation of the Earth. The drift will be allowed to gather. Perhaps, centuries from now, some future body will add a leap minute or a leap hour to bring the clocks roughly back in line with the sky. But the era of the leap second, the era of the small annual accommodation to an imperfect planet, is ending. The risk of subtracting a second was judged greater than the cost of letting the sun slip out of step. The engineers won, the sky lost. There is a quiet sadness in that outcome, and the people who work in timekeeping feel it, even if they are not sentimental by trade. They are physicists and metrologists, people who live among instruments and uncertainties. But they understand that the second is the most precisely measured quantity in all of human history. The newest optical clocks can hold time to within a fraction, so fine they would not gain or lose a single second across the entire age of the universe. And yet, with all that precision in hand, we have lost the thread to the planet. The Earth, our first clock, has become too irregular for our perfect machines to follow. So, we are letting it go, a millisecond at a time, And underneath the practical decision sits a question the delegates in Geneva understood but did not say aloud. The planet's wandering rotation is not only a nuisance for engineers, it is a symptom. The core is doing something we cannot yet model. The wobble has shifted. The magnetic field is weakening over the South Atlantic. The ice is leaving the poles. All of it is a planet entering a new regime, and the leap second is merely the most precisely measurable edge of that change. Which raises the question that the engineers cannot answer and that this story is really about. Is the glitch only here, in the spin of one small world? Or does it reach further out past the moon, past the sun, past the nearest stars into the timekeeping of the universe itself? To find out, you have to stop looking down and start looking up. The clock of the cosmos has a name. It is called the Hubble constant, and it measures how fast the universe is expanding, how quickly space itself is stretching, carrying the galaxies away from one another. If you know that rate, you can run the expansion backward, like rewinding a film, until everything is pressed back into a single point. Where the film begins is the beginning of time. So the Hubble constant is not only a measure of expansion, it is, in a real sense, the universe's age, written as a single number. And for the past decade, that number has refused to settle. We have measured it two different ways, with two of the most careful efforts in the history of science, and the two answers do not agree. The universe appears to be keeping two different times. It is worth remembering how hard won even a rough value was. When Edwin Hubble first measured the expansion at the Mount Wilson Observatory in the 1920s, the number he got was so large that, run backward, it implied a universe younger than the rocks of the Earth. A cosmos less than 2 billion years old, sitting inside a planet. Geologists knew to be older than that. It was a flat contradiction, and it told astronomers that something in the measurement was badly off. Over the following decades, the value was corrected and corrected again, as the distance scale was rebuilt, and the implied age of the universe drifted upward, settling somewhere between 10 and 20 billion years. That wide uncertainty was frustrating, but it was also comfortable. It left enough slack for everything to be reconciled quietly, without anyone having to confront a deeper problem. The trouble began only when the measurements grew precise, when the slack ran out. The first answer comes from the oldest light there is. When the universe was about 380,000 years old, it had cooled just enough for the first atoms to form, and in that instant, it became transparent. The light set free at that moment has been travelling ever since, stretched by the expansion of space into a faint microwave glow that fills the entire sky, cooled now to just 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of the beginning. It is not perfectly smooth. Imprinted on it are tiny variations in temperature, differences of a few parts in 100,000, and those ripples are a map of the infant universe, the seeds from which every galaxy would later grow. Read that map carefully enough and it gives up the fundamental numbers of the cosmos. To read it, the European Space Agency launched the Planck satellite in 2009. For 4 years it stared at the background radiation from a vantage point well beyond the moon, mapping the ripples with a precision no instrument had reached before. When the Planck team finished their analysis, they produced a value for the expansion rate of 67.4 kilometers per second for every megaparsec of distance. A megaparsec being about 3.25 million light-years, the uncertainty was less than 1%. From that number followed an age for the universe of 13.8 billion years. It was a triumph of precision. The error bars were small, the physics was consistent, and the cosmologists who produced it were confident the question was closed. The second answer starts not with the oldest light, but with the nearest stars, and it is built like a ladder. The first rung is parallax, the tiny shift in a nearby star's apparent position as the Earth swings from one side of its orbit to the other. The Gaia satellite, launched in 2013, measured that shift for more than 1 billion stars, fixing their distances with extraordinary care. That calibrates the second rung. Cepheid variable stars are aging giants that pulse in brightness, swelling and shrinking on a steady beat, and the length of that beat is tied directly to their true luminosity. Time how fast a Cepheid pulses and you know how bright it really is. Compare that to how bright it looks, and you know how far away it sits. The Cepheids in turn calibrate the third rung. Type 1a supernovae are the detonations of white dwarf stars, and because a white dwarf can only grow so heavy before it ignites a ceiling of about 1.4 times the mass of the Sun, these explosions all flare to nearly the same true brightness. They are standard candles bright enough to be seen across billions of light years. Each rung is calibrated by the one below it, and together they reach far enough out to measure the expansion of the local universe directly. The man who has spent the last decade hauling that ladder out into the dark is Adam Riess, an astronomer at Johns Hopkins University and the Space Telescope Science Institute. Riess is not a newcomer to overturning things. In 1998, he was part of one of the two teams that discovered the expansion of the universe is not slowing down, as everyone had assumed, but accelerating, pushed apart by the dark energy that no one can yet explain. He shared the Nobel Prize for that, and then he turned to measuring the expansion rate as precisely as the ladder would allow, with a project his team named SHOES. Year after year the measurement grew tighter, and year after year it sat stubbornly above the number from the oldest light. The most recent value from his team is 73.04 kilometers per second per megaparsec. Set the two numbers side by side. 67.4 from the infant universe, 73.04 from the universe as it is now. The gap between them is small in raw terms, under 6 kilometers per second per megaparsec, but both measurements are so precise that the gap towers over their combined uncertainty. The odds that it is a statistical accident have fallen below 1 in a million. In the language physicists reserve for the threshold of a real discovery, the disagreement has passed 5 standard deviations. This is not noise. It is a fact about the universe that we do not understand, and it has a name, the Hubble tension. Riess himself has called it a crisis, and he does not reach for that word casually. A Nobel laureate does not say crisis about the central measurement of his own field unless the data has cornered him, and the data keeps closing the exits. The most obvious escape was to blame the ladder to argue that the Cepheids in distant galaxies are so crowded by neighbouring stars that the old telescope could not cleanly separate their light, biasing the measurement. So in 2023, Riess's team turned the new James Webb Space Telescope on the same stars. Webb's sharper infrared vision could pick the Cepheids out of the crowd. The result confirmed the earlier work almost exactly. The local measurement held. The tension was not a flaw in the data. It was real, and it is not only Riess. The unsettling thing about the Hubble tension is how many separate roads lead to the same split. A collaboration that goes by the name Holy Cow used a completely different method measuring the delay between multiple images of a single distant quasar. Its light bent into separate paths by the gravity of a galaxy in front of it and arrived near 73. A project that timed water masers, natural microwave lasers orbiting the black holes at the hearts of distant galaxies, landed near 73 as well. Meanwhile, every method that probes the early universe clusters down near 67. The early universe measurements agree with each other. The late universe measurements agree with each other. They simply do not agree across the divide. There is one method, championed by Wendy Friedman at the University of Chicago, that measures distances using the brightest old red giant stars instead of Cepheids, and it lands in the middle, near 70, with error bars wide enough to shake hands with both camps. That middle value has not calmed the crisis. It has only made the map more complicated. The early universe camp, meanwhile, has more than the background radiation on its side. Spread through the distribution of galaxies across the sky is a faint, fossilized ruler, a preferred separation between galaxies, a little under 500 million light-years. That is the frozen imprint of sound waves rippling through the hot plasma of the infant cosmos before it cooled. Astronomers can measure that ruler in enormous galaxy surveys and use it to gauge the expansion entirely independently of the background radiation. And it agrees with the background radiation. It points to the same low value, near 67. So the disagreement is not one stubborn measurement against another. It is two separate windows onto the early universe, both saying one thing, against a whole family of measurements of the nearby universe, all saying another. The line does not fall between two instruments. It falls between two epochs. If the tension is real, and the weight of evidence now says it is, then the standard model of cosmology is incomplete. That model is called lambda cold dark matter, and it is one of the most successful theories ever written. It holds that the universe is about 5% ordinary matter, about 27% dark matter, and the rest dark energy. And from those few ingredients, it correctly predicts the pattern of the background radiation, the web of galaxies spread across the sky, and the proportions of the lightest chemical elements forged in the first minutes after the beginning. It works almost everywhere. It does not work here. Somewhere in the history of cosmic expansion, between the infant universe and the present one, something is missing. Whatever it is, it would have to do something specific. It would have to make the early universe expand a little slower than the model predicts, or the late universe expand a little faster, or both, so that the two clocks could be reconciled. One leading candidate is a fleeting burst of energy in the first 100,000 years, active just long enough to nudge the early expansion before fading away, what theorists call early dark energy. Another is that dark matter is not as inert as we assume, that it interacts in some way we have not detected. Another is that gravity itself, general relativity, does not behave on the largest scales exactly as Einstein wrote it. Each of these is being chased hard, and none has yet emerged as the answer. What gives the whole problem its weight is what is at stake in solving it. For most of the past few decades, cosmology has been a science of refinement, of measuring the known numbers ever more precisely, of confirming a model that kept passing every test. The Hubble tension is the first crack in that long success in a generation, the first place where the careful, settled picture has failed to hold under the weight of better data. If it survives and every attempt to make it go away has so far failed, then it is not a rounding error to be tidied up. It is a doorway. Whatever lies on the other side, whether it is a new form of energy in the infant cosmos, an unsuspected behavior in the dark matter, a flaw in our theory of gravity on the largest scales, or something stranger still, it would be the first genuinely new ingredient added to the recipe of the universe since dark energy itself was discovered. The disagreement over a single number is, in the end, a disagreement about whether we actually understand the history of everything. And the honest position, the one the most careful cosmologists hold, is that right now we do not. And then there is a possibility that is simpler than any of them, and far more unsettling. What if the Hubble constant is not constant, not because of some missing ingredient, but because time itself ran at a different rate when the universe was young? It sounds like a thing said for effect, but it has a serious history in physics, and a name: varying speed of light cosmology. Its most prominent advocate is João Magalhães, a physicist at Imperial College London, who has argued for decades that light travelled faster in the early universe and slowed to its present value as the cosmos aged. He proposed it first to solve a different puzzle: the strange uniformity of the background radiation across regions that should never have been in contact. But it carries a consequence for this one too. If light was faster in the past, then the early universe's clock effectively ran faster than ours, and a measurement that reaches back to that era would naturally disagree with one taken nearby. The mismatch would not be an error, it would be a fingerprint. Magalhães' idea is not part of the mainstream. The evidence that the speed of light has held constant is broad and deep, drawn from particle physics and from the light of distant quasars. But the Hubble tension has given theories of varying constants a foothold they did not have before, precisely because they offer a natural reason why two measurements taken at two different epochs would refuse to match. The physicists at the centre of this are careful with their words. They do not say that time is broken. They say the measurements are in tension, that the model may need extension, that new physics may be required. But sit with the data long enough and the implication is hard to avoid. The oldest light and the nearest stars are telling two different stories about how long the universe has been here. And if the universe cannot agree with itself about its own age, the comfortable assumption that time is a single fixed backdrop, the same for everyone, everywhere and everywhen, starts to look like exactly that, an assumption. Thank you for watching. One that something in the summer of 2022 was about to make a great deal harder to hold. The James Webb Space Telescope was built, more than anything, to see the first galaxies. The old Hubble telescope could look far back, but not far enough. The light from the very earliest galaxies, the ones that lit up in the first few 100 million years, has been stretched so severely by cosmic expansion that it has slid out of the visible range entirely into the infrared, where Hubble could not follow. Webb was built to follow it. Its primary mirror is 6.5 meters across, a segmented dish of gold-coated beryllium that gathers more than 6 times the light of its predecessor. Its instruments are chilled to within a few degrees of absolute zero, so that their own warmth does not drown the faint infrared whisper arriving from the edge of time. It is the most sensitive telescope ever pointed at the sky, and when it launched on Christmas Day, 2021, the astronomers who study the early universe held their breath. They expected to find small things. The Standard Model makes a clear prediction about how structure grows. In the beginning, the universe was a nearly featureless fog of hydrogen, helium, and dark matter. The dark matter, feeling only gravity, began to clump, drawing the ordinary gas into its gathering wells. The gas cooled and lit the first stars, enormous, short-lived, made of nothing but the lightest elements. Those stars gathered into small galaxies, and the small galaxies merged, slowly, over hundreds of millions of years, into larger ones. The process was supposed to be gradual and hierarchical, building from the bottom up. By 500 million years after the beginning, the largest galaxies should have been modest assemblies, a few 100 million times the mass of the Sun at most. Our own Milky Way, with its trillion solar masses and its great spiral arms, is the product of 13 billion years of patient growth. That kind of structure takes time. That was the prediction. In February 2023, a paper in the journal Nature broke it. The lead author was Ivo Labbé, an astronomer at Swinburne University of Technology in Melbourne. His team had been working through data from one of Webb's earliest surveys, staring at a patch of sky already well mapped by Hubble. And in that patch, at distances corresponding to roughly 500 to 700 million years after the beginning, they found 6 galaxies that were not modest at all. They were not small. They held stars adding up to as much as 100 billion times the mass of the Sun, comparable to the Milky Way today, a galaxy that has had 13 billion years to assemble itself. Some of them appeared to contain more stars than the available gas in their region could even have supplied. In the careful language of the paper, they were candidates for galaxies that challenged the standard picture. In an interview, Labbé put it more plainly. Finding them, he said, was like walking into a nursery and meeting a full-grown elephant. His team had a private name for them, the Universe Breakers. The reaction was a mix of exhilaration and unease. There were reasons for caution. The masses were estimated from brightness and colour, using models of the unseen stellar populations that are genuinely hard to pin down without detailed spectra. But if the estimates held, the Standard Model of galaxy formation was in serious trouble. There was simply not enough time in the accepted timeline for galaxies to grow that large. The dark matter wells at that early epoch were not supposed to be deep enough to gather so much gas. The rate at which stars would have had to form pushed against the limit of what is physically possible for a collapsing cloud. The galaxies should not have been there, and yet there they were, bright and unmistakable in Webb's images. They were not alone. Other teams, working through other patches of Webb data, kept finding similar objects. A large survey of the early cosmos turned up candidate galaxies even farther back, at distances corresponding to just 300 or 400 million years after the beginning, and some of these too looked surprisingly substantial. One candidate was first estimated to lie so far away that we would be seeing it just 250 million years after everything began, which would have made it the most distant object ever observed. That one came with a lesson attached. Follow-up measurements of its true spectrum revealed that its light had been contaminated by a nearer galaxy, and its distance collapsed to something far more ordinary. Estimating distance from colour alone, without a full spectrum, can deceive you, and the early universe is generous with traps. But other distant, massive candidates survived the scrutiny. Webb's spectrograph confirmed them. The pattern held. The early universe is more luminous, more built up, more grown than anyone had predicted, and the records kept falling faster than anyone expected them to. Even before Webb, the Hubble telescope had spotted a single galaxy, known by its catalogue name as GNZ11, that seemed to lie improbably far back, more than 13 billion years away, brighter and larger than a galaxy at that age had any right to be. It was treated, at the time, as a strange outlier. Then Webb arrived, and the outliers became a crowd. In 2024, the survey teams confirmed a galaxy seen as the universe turned roughly 290 million years old, and it was not a faint smudge, as a galaxy that early was supposed to be, but startlingly bright, with traces of oxygen in it that should have taken generations of stars to forge. A year later, that record fell too, to a galaxy confirmed at a redshift of 14.44. Its light leaving when the universe was only about 280 million years old, less than 2% of its present age. The team that found it called their paper a cosmic miracle, and noted, almost wearily, that the telescope seemed poised to keep breaking its own records, reaching back toward the era of the very first stars. Each of these galaxies, on its own, might be explained away. Together they form a pattern that the standard timeline strains to hold. There is a further oddity that Webb turned up, and no one yet knows what to make of it. Scattered through the deep images are small, intensely red points of light that astronomers have taken to calling little red dots. They are compact, far more compact than ordinary galaxies, and they appear in startling numbers in the early universe, and then largely vanish from later epochs. Some astronomers suspect they are not really galaxies at all, or not only galaxies, but the glow of gas falling into surprisingly large black holes that seem, like the galaxies around them, to have grown too big too fast for the standard account of how such things form. The little red dots are an open question, but they point in the same direction as everything else in this part of the sky. The early universe did its building more quickly, and on a larger scale than the clock we have been keeping says it should have been able to. This is a different problem from the Hubble tension, but it points the same way. The tension is a disagreement about a single number, the expansion rate. The impossible galaxies are a disagreement about the timeline of how structure forms. Both, in the end, suggest the same thing, that the standard model's clock is wrong, that the early universe either had more time to do its work than we thought, or that its work proceeded faster than our physics allows. There are several ways to answer that, and they range from cautious to radical. The most conservative is to question the mass estimates themselves. The total mass of stars in a distant galaxy is inferred from its light, using assumptions about what kinds of stars are shining. If the first galaxies were dominated by enormous brilliant stars, and there is good reason to think the earliest stars were far more massive than typical stars today, because the primordial gas lacked the heavy elements that let a cloud cool and fragment into smaller pieces, then the same amount of light could be produced by a smaller total mass than the simple models assume. This first generation of stars even has a name. Astronomers call them population 3 stars, forged from nothing but the hydrogen and helium left over from the beginning, before any heavier element existed anywhere in the universe. Those heavier elements, the carbon and oxygen and iron that everything since has been built from, did not exist yet, because they are made inside stars, and there had not yet been any stars to make them, and their absence shapes the whole story of how the first stars could form. Heavy elements are what allow a collapsing cloud of gas to shed its heat and cooling is what lets a cloud break into many small fragments, each becoming a modest star like our Sunday. Without them, the primordial clouds could not cool efficiently, could not fragment, and so collapsed instead into a small number of giant stars, perhaps hundreds of times the mass of the Sun, blazing blue-white and burning through their fuel in just a few million years before detonating. No example of a population 3 star has ever been directly seen. They are too far, too faint, too long gone, but they are a necessary chapter. The bridge between a universe of bare gas and the chemically rich cosmos we live in, and the strange brightness of the early galaxies may be partly their signature. Catching one, unmistakably, is among the things the great telescopes are now straining to do. That would soften the problem. It would not erase it. Even allowing for unusual early stars, several of these galaxies remain hard to explain, and the difficulty is not only their mass but their structure. Some appear to have organized, settled forms, disks, even faint hints of spiral arms, and that kind of order is supposed to take time to assemble. The next answer is to modify the standard model itself. Perhaps dark matter has properties that let structure gather faster. Perhaps the early universe was clumpier in places than the smooth average suggests, seeding galaxies ahead of schedule. Perhaps there is an ingredient in the cosmic recipe we have not yet named. Theorists are producing papers at a furious pace, proposing new behaviors in the dark sector and new wrinkles in the early expansion, and none has yet stepped forward as the clear solution. And then there is the most radical answer of all, the one that loops this back to the heart of the matter. What if the universe is simply older than we think, not because of a mismeasured expansion rate, but in plain, absolute years. This is the proposal Rajendra Gupta, a physicist at the University of Ottawa, published in 2023. Gupta combined two ideas that have long sat at the edges of cosmology. The first is tired light, the old notion that light loses energy slowly as it crosses vast distances, redshifting, not because space is expanding, but because of some interaction with the vacuum it travels through. Tired light was first floated by Fritz Zwicky in 1929, and it has been set aside many times since, because on its own it cannot account for the background radiation or for the way distant supernovae visibly play out in slow motion. The second idea is that the fundamental constants of nature have drifted over cosmic time. Stitch the two together, and Gupta builds a universe that is 26.7 billion years old, nearly twice the standard age. In that universe, the impossible galaxies are not impossible. They are simply old. They had the time. Gupta's model is not widely accepted, and it would be misleading to suggest otherwise. Most cosmologists regard tired light as ruled out by several independent lines of evidence, and the drift of the fundamental constants is held to a tiny margin by laboratory measurements and by the spectra of distant quasars. But the paper is useful in one honest way. It makes explicit what the more cautious work leaves between the lines. The data coming back from Webb is pressing on the boundaries of the standard model hard enough that even ideas long thought settled are being pulled back onto the table and looked at again. When the observations insist that something is wrong with the timeline, you are forced, at least, to consider that the timeline itself is the thing that is wrong. The other way to handle the strain between early and late, rather than adding years to the universe, is to let the rate of time change, and here, Magajo's varying speed-of-light cosmology returns. In his picture, the early universe is not older in our years, but its years are different. A clock placed in the first few 100 million years would tick faster than a clock placed today. The processes that take 1 billion years by our present reckoning, stars igniting, galaxies assembling, gas enriching with heavier elements, might take only a few 100 million years by the clock of the young cosmos. The universe breakers would then be exactly what you would expect from a universe that was, in its youth, in a hurry. The idea remains speculative. New experiment has confirmed it, but the impossible galaxies have made it a question that has to be asked, rather than one that can be waved away. There is a thread running under all of this, and it is worth naming before we follow it. Every one of these proposals, the older universe, the faster early clock, the missing ingredient, is reaching for the same intuition, that the rate of time might not be the same in all places and at all epochs. It sounds exotic. It sounds like a thing you would only entertain when the data left you no choice. But in fact, the universe has been telling us, plainly and for over a century, that the rate of time is not fixed. It told us through a man sitting in a patent office in Bern, thinking about what would happen if he chased a beam of light. We did not need a telescope to find it. We only needed to take his equations seriously. The special theory of relativity, which Albert Einstein published in 1905, rests on a single, ruthless insight. The speed of light is the same for every observer, no matter how fast they are moving. That sounds harmless. It is not. If the speed of light never changes, then something else has to give, and what gives is space and time themselves. Two people moving relative to one another will disagree about the length of a ruler and the duration of a second, and they will not be making a mistake. The disagreement is physical. A clock moving quickly past you genuinely ticks slower than your own. A ruler moving quickly past you genuinely shrinks along its direction of travel. These effects are far too small to notice at the speeds of ordinary life, but they grow without limit as you approach the speed of light, and they are not a quirk of the equations. They are measured. There is a consequence of this that is stranger than the slowing of clocks, and it strikes at the very heart of what we mean by time. It is called the relativity of simultaneity. If the speed of light is the same for everyone, then two observers moving relative to one another will not agree on whether two distant events happened at the same time. One will say the events were simultaneous. The other, moving past, will say one clearly came before the other, and neither is wrong. There is no master clock ticking over the universe, no shared present moment that everyone everywhere is passing through together. The idea of now this instant, happening everywhere at once, turns out not to be a feature of the universe at all. It is a feature of a single point of view. Your now and the now of someone speeding past you slice through reality at slightly different angles, and the faster the relative motion and the greater the distance, the more those slices diverge. For two people walking past each other on a street, the disagreement is unimaginably tiny, a sliver of a second across the width of a galaxy. But it is not zero, and it is not a matter of opinion. It is built into the structure of space and time. The universal present that we feel so certain of, the sense that the entire cosmos shares this one moment with us, is something our minds supply. The physics does not contain it. The cleanest demonstration falls out of the sky constantly. When cosmic rays strike the upper atmosphere, they create showers of particles called muons, and a muon is unstable. Left to itself, it survives for only about 2/millionths of a second before it decays far too short a life to cross the tens of kilometers of atmosphere and reach the ground. By every reasonable calculation, almost none should make it down, and yet they pour through us in great numbers. Several pass through your body every second. The reason is that the muons are moving at nearly the speed of light, and from our point of view, their internal clocks run slow, stretching that brief life just enough to carry them to the surface before they expire. The muon does not feel anything unusual. In its own frame, it lives and dies on schedule. The stretching is entirely relative and entirely real. The most famous illustration of this is the story of the twins, and it is not just a story, it is what the equations plainly require. Take two identical twins. One stays home on Earth, the other climbs into a ship, races out toward a distant star at close to the speed of light, turns around, and comes home. When the traveller steps off the ship, they are younger than the twin, who stayed not as a trick of perception, but in the plain count of birthdays, in the greying of hair, in the cells of the body. The travelling twins' clock genuinely ran slow during the journey, and they have lived through less time than their sibling. If the speeds were extreme enough, the traveller might return after what felt to them like a few years to find that decades, or centuries, had passed at home. This is not science fiction borrowing from physics. It is physics, confirmed in miniature every time an unstable particle in an accelerator lives longer than it should, because it is moving fast, and confirmed directly with atomic clocks flown on aircraft and carried aboard spacecraft. Fast travel is, quite literally, a form of time travel into the future. The faster you go, the further ahead you arrive, and you can never come back. The price of the journey is paid in the time of everyone you left behind. Then, in 1915, Einstein extended the insight from motion to gravity, and the picture deepened. Gravity, he showed, is not a force pulling objects together across empty space. It is the curving of spacetime by the presence of mass and energy. A heavy object like the Earth or the Sun bends the geometry around it, and everything nearby, light, planets, time itself, follows that bend. And because time is woven into the geometry, where the geometry curves, time curves with it. The deeper you sit in a gravitational field, the slower your clock runs. A clock at sea level ticks slower than a clock on a mountaintop. The difference is minute, but it is not theoretical. It has been measured again and again by people who set out specifically to catch it. The first to catch it in a laboratory were two physicists at Harvard, Robert Pound and Glenn Rebka, in 1959. They sent gamma rays up a tower in the physics building, a climb of about 22 meters, and measured the tiny shift in the radiation's frequency as it rose out of the Earth's gravity. The shift was almost unimaginably small, a few parts in 1,000 trillion, and they measured it anyway, confirming that time at the top of the tower ran very slightly faster than at the bottom. A decade later, in 1971, two American researchers, Joseph Haefele and Richard Keating, did something almost comically direct. They bought tickets for 4 atomic clocks and flew them around the world on ordinary commercial airliners, once heading east, once heading west, then brought them home and compared them to clocks that had stayed on the ground. The flying clocks disagreed with the stationary ones, by fractions of a millionth of a second, in exactly the amounts that relativity predicted once you accounted for both their speed and their altitude. Time really had passed differently for the clocks that flew. Most people carry a far more powerful proof of all this in their pocket, and use it every day without a thought. The Global Positioning System is a constellation of satellites circling the Earth at an altitude of about 20,200 kilometers, each carrying an atomic clock, each broadcasting the time. Your phone works out where you are by comparing the signals from several of them and calculating, from the tiny differences in their arrival, how far you sit from each. But those satellite clocks are caught between the two halves of relativity. Because the satellites move fast relative to the ground, special relativity slows their clocks by about 7 millionths of a second per day. Because they orbit high above us, where gravity is weaker and time runs faster, general relativity speeds their clocks up by about 45 millionths of a second per day. The two effects do not cancel. The net result is that each satellite clock gains about 38 millionths of a second every day relative to the ground. 38 millionths of a second sounds like nothing, and in a human life it is nothing. But light travels about 30 centimeters in a billionth of a second, and in 38 millionths of a second it travels more than 11 kilometers. If the system simply ignored relativity, the position it reported would drift by that much every single day. Within a couple of hours, your navigation would be visibly wrong. Within a day, it would be useless, sending you to the wrong city. The engineers who built the system knew this, and so they built the correction in from the start, tuning the satellite clocks before launch to run at a rate that looks correct only once they are up in weaker gravity, moving fast. The fact that your phone can tell you which street you are standing on is a working, daily confirmation that time runs at different speeds at different heights. General relativity is not a curiosity in a textbook, it is a maintenance requirement. And the effect does not stop at orbital altitudes. It reaches down to the scale of a human body and then below it. In 2010, a team at the National Institute of Standards and Technology in Boulder, Colorado, led by Chin-Wen Chao, took two of the most precise clocks ever built and raised one of them just 33 centimeters above the other, about the height of a single step. And they measured the difference. The higher clock, sitting a third of a meter closer to the sky, ticked detectably faster. The shift was about 4 parts in 100 quadrillion, a number so small it barely holds meaning, and they read it cleanly. The experiment proved that relativity bends time across a distance smaller than a person is tall. If you are standing up right now, your head is aging very slightly faster than your feet. Then, in 2022, a group led by Junye at a laboratory in Boulder, run jointly by that same Standards Institute, and the University of Colorado pushed the measurement further still. Using an ultra-precise optical clock built from a cloud of strontium atoms, they detected the difference in the flow of time across a single millimeter of height, the thickness of a fingernail. Across a gap you could barely see, the top of the atom cloud aged faster than the bottom. This is now the finest scale at which we have ever caught time bending under gravity. It is happening everywhere, all the time, at every height, for everything. We simply never built instruments delicate enough to see it until now. If the Earth, a modest planet, warps time enough to measure across a fingernail's width, the natural question is what happens near something far heavier. The answer was worked out by Carl Schwarzschild in 1916, only months after Einstein published the general theory. While Schwarzschild was serving on the Russian front in the First World War, he solved Einstein's equations for the simplest case imaginable, a single, round, non-rotating mass, and his solution contained something monstrous. If you could compress a given mass into a small enough radius, the curving of spacetime around it would become so extreme that time, as seen from outside, would slow to a complete stop. That radius is now called the Schwarzschild radius, and it marks the point of no return. For the Earth, it is about 9 millimeters squeeze the entire planet into a sphere smaller than a marble, and it would become a black hole. For the Sun, it is about 3 kilometers. The surface at that radius is the event horizon, and it is not a wall. There is nothing there to touch, nothing there to see. It is a boundary defined purely by geometry, the distance from the center at which the speed needed to escape rises to the speed of light, so that not even light can climb back out. And the strangest thing the equations predict happens to time at that edge. Picture it for yourself. You are falling toward a black hole, feet first, and somewhere far behind you a colleague is watching through a telescope, recording everything. From where you are, nothing about your own time feels wrong. Your watch ticks 1 second per second. Your heartbeat is steady. The horizon looms ahead, growing, and you fall toward it at what feels like an ordinary, terrible acceleration. You cross it without any sensation at all. No wall, no barrier, just a place you are now on the wrong side of. But your colleague sees something entirely different. To them, your fall slows as you near the horizon. Your watch, carried in the light you send back, ticks slower and slower. The light itself reddens and dims, stretched by the gravity it is climbing out of. You appear to ease toward the edge and never quite arrive. You hang there, frozen in the last instant of your descent, growing fainter and redder for the rest of time, a fading image pinned to the boundary forever. From inside, you are already gone. From outside, you never leave. Both are true. Time has simply split between you, and if you could turn and look outward as you fell, the universe behind you would not be frozen. It would race. The deeper into the well you go, the faster the outside cosmos runs. Stars wheel through their lives. Galaxies drift and merge. If the black hole were large enough, one of the supermassive giants, whose horizons are so vast that the tidal stretching there is gentle, you could, in principle, fall for what feels to you like a finite span and watch the entire future history of the universe play out above you, sped to a blur before you reach the center. Inside the horizon, the equations do something even stranger. Space and time trade roles. The direction pointing inward, toward the center, becomes a direction in time, just as you cannot avoid moving forward into next week out here. In there, you cannot avoid moving toward the center. The singularity is not a place you might steer around. It is a moment in your future, as fixed and unavoidable as tomorrow. For a long time, all of this lived only in the mathematics, and it was reasonable to wonder whether nature actually built such things, or whether they were artifacts of a too-perfect equation. Then, in April 2019, the Event Horizon Telescope released the first direct image of a black hole, the supermassive one at the center of the galaxy, Messier 87, 53 million light-years away. The image was assembled from radio telescopes scattered across the planet, linked together into a single instrument the size of the Earth. It does not show the horizon itself, which emits nothing, but the glowing ring of matter bent around it, with the dark shadow of the hole carved out of the middle. It was a confirmation, written in light, that the extreme bending of time predicted a century earlier on a battlefield is not a fantasy. It is out there, 53 million years away, a place where time, for any observer watching from a safe distance, has effectively come to a halt. Closer to home, at the center of our own galaxy, we have caught time bending around a black hole in real time. There sits a supermassive black hole, some 4 million times the mass of the Sun, and a handful of stars orbit it on tight, swift paths. One of them, known simply as the second star in the cluster, swings around the black hole every 16 years, and at its closest approach, it whips past at a few % of the speed of light, skimming the deep gravitational well. In 2018, as that star reached the bottom of its plunge, a team operating a set of linked telescopes in Chile measured the color of its light with exquisite care and watched it redden, exactly as general relativity demands. As the light climbed out of the black hole's gravity and lost energy in the climb, the star's clock had slowed, measurably, at the pit of its orbit, and then sped back up as it swung away. We did not infer it from theory. We watched a star fall toward a monster, saw its light go red with the strain, and saw it recover. The bending of time is not only 53 million light-years away, it is at the heart of the galaxy we live in, and we have now seen it happen. So the universe was already telling us, long before the Hubble tension and the impossible galaxies, that time is not a fixed backdrop. It is a physical thing, shaped by mass, stretched where matter gathers and slowed where it gathers most. And if a single planet bends time across a fingernail, and a single dead star can stop it altogether, then the whole sky, strewn with mass, must be a landscape of clocks all running at slightly different rates. The next question is whether we can see that landscape. As it turns out, we can. The universe writes the bending of time directly into the light that reaches us, if you know how to read the delays. If gravity bends time, then it also bends the path of light, because light must follow the curving geometry it travels through. And this turns the whole universe into a kind of lens. Canotry 19. A massive object, a galaxy, or a whole cluster of galaxies warps the space around it, and light from anything behind it does not come to us straight. It bends around the mass, the way light bends through the base of a wine glass and arrives distorted, magnified, sometimes split into several images of the same distant thing. Each of those images is built from light that took a different route through the warped region, and the routes are not the same length. The light along them arrives at different times. The universe shows us the same event more than once, at more than one moment. This was predicted before general relativity was even finished. Einstein worked out that the sun's gravity should bend the light of stars passing near it. And in 1919, Arthur Eddington went to an island off the coast of West Africa to test it during a total eclipse. When the stars near the darkened sun could be photographed, their positions had shifted by just the amount the theory demanded. The sun's gravity had bent their light, and Einstein became famous overnight. But it took decades for the full power of the idea to emerge. Bending light is not only a test of relativity, it is a tool. A massive foreground object becomes a natural telescope, magnifying what lies behind it. And when the alignment is close to perfect, a single distant galaxy or quasar can appear as multiple images arranged in arcs or crosses around the lens. The most remarkable demonstration of this involved a single exploding star and a prediction that should not have been possible to make. Behind a massive galaxy cluster some 5 billion light-years away in the constellation Leo, there sits a much more distant galaxy, more than 9 billion light-years off. In late 2014, astronomers using the Hubble telescope saw a supernova flare up in that distant galaxy, and they saw it not once, but 4 times over. Its light split by the gravity of a single galaxy within the cluster into a cross of 4 images surrounding it. They named the supernova Refsdal, after Sjur Refsdal, the Norwegian astrophysicist who, back in 1964, had first suggested that a lensed supernova could be used to measure the universe. Patrick Kelly, an astronomer then at the University of California, Berkeley, led the discovery, and he and his colleagues realized something extraordinary. The 4 images were not the only ones the cluster would produce. Their model of how mass, including the invisible dark matter, was distributed through the cluster, told them that some of the supernova's light had set out along a longer path, one that wound through a denser region of the cluster, and that this delayed light had not arrived yet. It was still on its way. The model predicted that a 5th image of the same explosion would appear in a specific place at a specific brightness, roughly a year later. They published the prediction, and then they did the only thing they could. They waited. In December 2015, they pointed Hubble back at the cluster. The 5th image was there in the predicted place, at the predicted brightness, right on schedule. No one had ever before forecast the reappearance of a supernova by modelling the curved space its light was crossing. The 5th image arrived about a year after the first 4, in our reckoning, but that 1 year of delay encoded a path difference of thousands of light-years, carved by the gravity of a single cluster bending the time of light that had already been travelling for over 9 billion years. The universe had let the same star explode twice for us, a year apart, because its clocks do not all run at the same rate. That same principle, that mass delays light, scales all the way up to the largest structures we can map, though there it grows mysterious. We are not sitting still. The Milky Way belongs to a small cluster of galaxies, which belongs to a larger supercluster, which belongs to a still vaster structure that astronomers, mapping the local cosmos in 2014, under the lead of Brent Tully, named Laniakea, a Hawaiian word meaning immense heaven. And all of it is in motion. Back in the 1970s, astronomers noticed that the background radiation was not the same temperature in every direction. It was very slightly warmer on one side of the sky and cooler on the opposite side, exactly the pattern you would expect if our entire local neighbourhood were moving through the radiation at about 600 kilometers per second. Something was pulling us. The direction pointed toward a region in the constellation Centaurus, a couple of 100 million light-years away, and astronomers gave the unseen pull a name: the Great Attractor. The Great Attractor is not one object. It is an enormous concentration of mass galaxies and clusters, and the dark matter holding them dense enough that its gravity steers the motion of everything for hundreds of millions of light-years around it, ourselves included. We are not falling into it the way a stone falls down a well. We are drifting with a whole river of galaxies, all sliding together toward the same distant centre of mass. And because we move through space at 600 kilometers per second, Our local clock runs ever so slightly slow compared to an imagined observer sitting perfectly at rest against the background radiation. It is the same time dilation that nudges the satellite clocks overhead, only written across the scale of superclusters, far too small to feel. But it means our own experience of time is faintly shaped by the gravitational geography of the cosmos we happen to inhabit. The map of that geography turned out to be grander than the Great Attractor alone. When Brent Tully's team traced the motions of thousands of galaxies and drew the watershed of our local flows, the boundary within which everything drains toward the same basin, they found that our home supercluster, Laniakea, stretches across something like 500 million light-years and gathers up the order of 100,000 galaxies. The Milky Way sits out near its edge, not at any center, drifting inward with the rest. And then, a few years later, the same kind of mapping revealed that we are not only being pulled, we are also being pushed. On the opposite side of the sky from the Great Attractor lies a vast region with less than the average amount of matter in it, an emptiness. Astronomers named the dipole repeller. A void does not pull, it simply fails to pull, and so a galaxy sitting between a dense region and an empty one is drawn toward the density and, in effect, shoved away from the emptiness. Our motion through the cosmos is the sum of a tug from a crowd of distant galaxies and a push from a great hollow on the far side. We are riding a current set up by where the matter is and where it is not, and our local clock keeps its slightly slowed time as we go. Beyond the Great Attractor, there was for a while a hint of something even larger and stranger. In 2008, Alexander Kashlinsky, an astrophysicist at one of NASA's research centers, reported that he and his colleagues had detected what they called dark flow. Measuring the motion of hundreds of distant galaxy clusters by the faint imprint they leave on the background radiation as they move, they found that the clusters seemed to be drifting together, coherently, in a single direction, as though something beyond the edge of the observable universe were drawing them. The pull pointed roughly toward the same patch of sky as the Great Attractor, but immeasurably farther, beyond the horizon of everything we can in principle ever see. If it were real, it meant the observable universe was not a sealed box. It was being tugged by structures outside it, so vast their gravity could be felt across the entire span of what we call the cosmos. The claim was contested from the moment it appeared. The signal Kashlinsky was chasing is extraordinarily faint and brutally hard to separate from noise, and he himself presented it cautiously. When the Planck satellite, with its sharper eyes, examined the same kind of data, it found no convincing evidence for the flow. The motion looked, in the end, like a statistical ghost, a pattern the earlier instruments' limits had conjured out of randomness. By the latter half of the 2010s, most cosmologists had set dark flow aside, and yet the episode left something behind worth keeping. Not a confirmed structure beyond the horizon, but a sharpened awareness that the edge of the observable universe is not the edge of the universe, and that what lies past it, forever beyond our sight, may still reach in and shape the space and the time of the small region we call home. There is one more kind of clock written into the sky, and it is the most precise natural timekeeper known. When a massive star dies and its core collapses into a neutron star, that core can be left spinning, sometimes hundreds of times a second, sweeping beams of radiation around like a lighthouse. From Earth, we catch each sweep as a pulse, and for certain of these pulsars, the pulses arrive with a regularity that rivals our best atomic clocks. They are, in effect, a network of natural clocks scattered across the galaxy, ticking with astonishing steadiness for millions of years. And in 2023, after 15 years of patient watching, several teams of astronomers around the world announced that those clocks were very slightly out of step, not randomly, but in a correlated pattern across the whole sky. The most natural explanation is that the entire Earth, and the pulsars too, are being gently rocked by a background of gravitational waves washing through the galaxy, stretching and squeezing the space between us and each pulsar, lengthening and shortening the time its pulses take to arrive. Most of those waves are thought to come from pairs of supermassive black holes, spiraling toward each other at the hearts of distant galaxies over spans of millions of years. We are, in a sense, hearing the slow groan of spacetime itself read off the ticking of dead stars. The achievement is worth pausing on. It took the better part of 2 decades, and it required treating dozens of pulsars scattered across thousands of light years as a single instrument. A detector effectively the size of our corner of the galaxy. Separate teams on different continents, watching different patches of sky, built up their records independently and then compared them, and the same faint pattern emerged in all of them. The waves they are sensing are nothing like the sharp chirps that ground-based detectors catch when two stellar black holes collide in a fraction of a second. These are waves with periods of years, slow undulations in the geometry of space, most likely the combined murmur of countless pairs of supermassive black holes circling one another across the universe, each pair taking millions of years to complete a single orbit. The signal is not one event but a sea of them, overlapping, a low background hum of gravity that washes through everything, including us. We do not feel it. The stretching and squeezing it works on the space around us is fantastically small, but the pulsars feel it, and by reading the slight wandering in the arrival of their pulses, we have begun, for the first time, to hear it too. And every part of it, the lensed supernova, the river of galaxies, the rocking pulsars, is the same lesson in a different key. Time is local. Time is shaped by mass and motion. The universe is not one clock but a vast field of them, each keeping its own slightly different now. But all of this still lives at the large scale, the scale of stars and galaxies and clusters, where the physics is smooth and continuous, and, however strange, still recognizable. There is another scale, the scale of the very small, where time stops behaving like a landscape at all, and starts behaving like something that may not be fundamental, that may not, at the deepest level, exist. Quantum mechanics is the most precisely tested theory in the history of science. It describes the behavior of atoms and the particles inside them with an accuracy confirmed to better than 1 part in a trillion. It underlies all of chemistry, almost all of modern technology, the structure of every element in the periodic table. And nearly a century after it was written down, physicists still do not agree on what it means. The mathematics is flawless and undisputed. The interpretation is a battlefield, and nowhere is that disagreement deeper than on the question of what quantum mechanics says about time. The first crack appears in a phenomenon called entanglement. When two particles interact in the right way, their states can become linked so that they can no longer be described separately, no matter how far apart they later travel. Measure one, and you instantly know something about the other even if it now sits on the far side of the galaxy. The link is real. It has been demonstrated in thousands of experiments, beginning with John Clauser in the 1970s, sharpened by Alan Aspect in the 1980s, and sealed in 2015 by 3 separate teams who closed the last remaining loopholes at once. Their experiments ruled out the comfortable possibility that the particles had simply carried hidden instructions with them from the start, agreed upon at the moment they parted. They had not. The correlation is established at the instant of measurement, across any distance, with no signal passing between them and no time elapsing in the crossing. In 2022, the Nobel Prize in Physics went to Clauser, Aspect, and Anton Zeilinger for this work. The citation was carefully worded. The implication was not. In a universe where entanglement is fundamental, the idea that space and time are the basic scaffolding on which everything else is built becomes very hard to hold. It is important to be precise about what entanglement does not do. It does not let you send a message faster than light. The outcome of any single measurement is random. You see your particles spin one way or the other, with no control over which and your distant partner sees their own random result. It is only afterward, when the two of you compare notes through ordinary signals that crawl along at the speed of light or below, that the correlations appear. The randomness protects cause and effect. No information outruns light. But the correlation itself is there, instant and undeniable, with nothing travelling between the 2 points to carry it. In a way that resists being put cleanly into words, the two particles were never quite two separate things. They were one system, spread across the gap, and the measurement did not act on one and then the other. It acted on the whole. If entanglement unsettles our sense of space, what quantum mechanics does to time is stranger still. Consider an experiment first dreamed up by John Wheeler in 1978, and actually performed by a team led by Jean-François Roche in 2007. It is a version of the famous double-slit setup. Send a single particle of light toward a barrier with 2 openings, and if no one checks which opening it passes through, It behaves like a wave going through both at once and building up an interference pattern, the signature of something that took both paths. But place a detector to catch which slit it really went through, and the wave behavior vanishes. The particle picks one slit, like a tiny pellet, and the interference is gone. Wheeler's twist was this. What if you wait? What if you delay the choice of whether to check the path until after the particle has already passed the slits? In the 2007 realization, the decision of whether to look was made by a quantum random process while the light was already most of the way through the apparatus, long past the slits, and the light's behavior matched the choice that had not yet been made when it passed through. Look for a path, and it had behaved like a particle that took one. Decline to look, and it had behaved like a wave that took both. The future setting seemed to reach back and fix what the light had already done. And, in the standard reading of quantum mechanics, this does not actually break cause and effect. The light is described by a wave that is not a physical thing moving through space, but a mathematical account of possibilities, and those possibilities only become a single definite reality when a measurement is made. Making the measurement later does not rewrite the past. It only settles which of the possibilities was real all along. But notice that the words I just used, possibilities, the wave, settling into reality, are themselves an interpretation. One way of speaking, among several, and not the only one. There is another, proposed by John Cramer in the 1980s, called the transactional interpretation, in which a particle sends a wave forward in time, and the detector sends a wave backward in time, and a handshake between the two, between future and past, determines what happens. In that picture, the future genuinely does participate in fixing the past, built into the structure of every quantum event. It is not the mainstream view, but it is fully consistent with every experiment ever done, which is precisely the discomfort. The equations do not single out a direction for time. We bring that direction with us. Underneath all of this sits the oldest open wound in quantum mechanics, the one called the measurement problem. Between measurements, a quantum system is described by a smoothly evolving wave of possibilities, and that evolution is perfectly reversible in time, as lawful backward as forward. But the moment a measurement is made, the wave appears to collapse. The many possibilities snap down to a single result, and that snapping is abrupt, random, and pointedly not reversible. Two utterly different kinds of behavior, stitched together, and no agreement on what the stitch actually is. Some physicists hold that the collapse is a real physical event we have yet to fully describe. Others, following the many worlds interpretation first proposed by Hugh Everett in the 1950s, say there is no collapse at all, that the wave never snaps down, that every possible outcome simply happens, each in its own branch of a perpetually splitting reality, and that we only ever notice the branch we happen to be riding. In that picture, the irreversibility we feel is an illusion of perspective, a consequence of which branch we find ourselves in, and the underlying physics remains as time-symmetric as ever. Still others propose that the particles always had definite positions, guided by a hidden wave, and that the randomness is only our ignorance. Every one of these interpretations fits the data identically. They cannot be told apart by any experiment yet devised, and they disagree profoundly about whether the flow and the irreversibility we take for granted are features of the world or features of our view of it. A later experiment pushed the strangeness even harder. In the year 2000, Yoonho Kim and his colleagues performed what is called a delayed choice quantum erasure. A particle of light is split into two entangled partners. One races off to a detector and is recorded. The other travels a longer route, and along that route the experimenter can choose after the first partner has already been detected, and its fate written down whether to preserve or erase the information about which path was taken. When the information is erased, the already recorded partner shows the interference pattern of a wave. When the information is kept, the interference is gone. The choice is made after the first particle's result is in the books. The recorded past appears to depend on a choice made in its future, and once again, no message travels backward. The pattern only reveals itself when you go back and correlate the two sets of records afterward, but the experiment has become one of the most cited reasons to suspect that, down at this level, time does not have a built-in direction at all. The orderly march from cause to effect, from past to future, that feels like the most basic fact of existence, is simply not written into the equations that govern the small. This has led some physicists to a radical conclusion that time is not a fundamental ingredient of reality at all, that it is something that emerges, at our large and clumsy scale, out of a deeper layer where there is no time. The most developed version of this comes from Carlo Rovelli, an Italian theorist and one of the founders of an approach to quantum gravity called loop quantum gravity, the central equation of quantum cosmology, the one meant to describe the universe at the very smallest scale, where quantum mechanics and gravity finally meet, has a famous and disturbing feature. It contains no time. There is no variable in it for the passage of moments. It describes a universe that simply is a vast frozen web of relationships among its parts, with no evolution and no flow. Time, in Rovelli's reading, is not something the universe has. It is something the universe does. It emerges from the statistical behavior of enormous numbers of interacting parts, the way temperature emerges from the jostling of countless molecules, none of which is itself hot. It is a thermodynamic effect, not a fundamental one. If the deepest equation contains no time, the obvious question is where our vivid sense of time comes from. And there is a striking answer, proposed in 1983 by Don Page and William Wouters. Their idea was that time emerges from entanglement. Imagine the universe split into two parts, a clock and everything else, and imagine the two entangled. Taken as a whole, the system never changes. It sits there, frozen and timeless, exactly as the equation demands. But ask what the rest of the universe looks like for each particular reading of the clock, and you recover change. Correlate the state of the world with the state of the clock, and the world appears to evolve from one clock reading to the next. Time, in this picture, is not something the universe moves through. It is the name we give to the correlations between a clock and the things it is entangled with. From outside, nothing happens. From inside, tied to the clock, a whole history unfolds. For 3 decades, this was pure theory, untestable, a curiosity. Then, in 2013, a group of physicists in Turin built a tiny model of it on a laboratory bench, using a pair of entangled photons, one playing the role of the clock, the other the role of the evolving universe. To an observer who measured the system from the outside, comparing it against an external reference, nothing about it changed. It looked static, timeless. But to an internal observer, one who read the clock photon and asked about the other in relation to it, the second photon visibly evolved. The same system was frozen from without and flowing from within. It was a model, a toy, 2 particles standing in for a cosmos, but it made something concrete that had seemed like pure philosophy. End quote. 9. Time may be what entanglement looks like from the inside. The idea is less alien than it first sounds. Look at a photograph. It shows a single frozen moment, and yet the photograph itself, the paper, the ink, exists in time, sitting in a drawer, yellowing. The deepest equations suggest something more extreme, that the entire universe, at the bottom level, is like a photograph with no outside, no drawer, no time in which it sits. There is only the structure of the correlations among its parts, all at once. The feeling of flow, the sense that the past is gone and fixed and the future is open and coming, would then be something that arises from the way we, who are ourselves part of the web, interact with the rest of it. We do not move through time, we are caught in a network of relations, and the appearance of flow is a feature of our limited view from inside. This is the block universe, an idea that grows out of relativity and finds an even deeper home in quantum gravity. In the block universe, every moment, every past, every present, every future is equally real. The beginning is not gone. It is as real, right now, as this moment. The far future, trillions upon trillions of years from now, is as real, right now, as this moment. The flow we feel is a fact about minds, not a fact about physics. It is worth sitting with how strange this is, because it cuts against the most basic feature of being alive. To us, the present moment is special, vivid, real, the only time that exists, with the past sealed away behind it and the future not yet arrived. But relativity has already told us there is no universal present, no single slice of now shared across the cosmos. And if there is no universal now, then the feeling that this moment is uniquely real, that it is lit up in a way that yesterday and tomorrow are not, cannot be a fact about the universe. It can only be a fact about us, about how a particular kind of memory-forming, forward-facing creature experiences its own existence from the inside. The physicist Hermann Weyl put the conclusion as plainly as anyone ever has, writing that the objective world simply is and does not happen. Nothing flows. The flow is what it feels like to be a small part of a structure that, taken whole, just exists, all of its moments at once. Einstein himself, late in his life, on the death of a dear friend, wrote to the man's family that the distinction between past, present, and future is only a stubbornly persistent illusion. He was not offering empty comfort. He was stating what his own physics had told him. The equations of the deep universe are symmetric in time. They run as happily backward as forward. The one thing that does point to the reason eggs break and never unbreak, the reason we remember the past and not the future, is the slow, statistical rise of disorder. And that arrow, the only arrow there is not a law of nature in the way that the conservation of energy is a law. It is a tendency. An overwhelming, near-certain tendency, but a tendency all the same, and it has a beginning and a cause, and someday an end. To understand the one direction time actually has, you have to leave the quantum world and follow that arrow back to where it was forged in the work of a man who died never knowing he had been right. The arrow of time points forward. It has always pointed forward, for every human being who has ever lived, and yet the deepest laws of physics do not require it to. The equations of motion, whether Newton's or Einstein's, work equally well run in either direction. A planet circling a star looks perfectly lawful whether the film runs forward or backward. The interactions of particles are very nearly symmetric in time, with one tiny exception buried in the weak nuclear force that has nothing to do with why a dropped glass shatters and never reassembles. So the forward direction we feel so certainly is not handed to us by the fundamental laws, it is added by something else. And that something is one of the most profound and most misunderstood ideas in all of physics. It comes from a man named Ludwig Boltzmann, born in Vienna in 1844, who spent his career trying to work out what heat actually is. The prevailing view when he began was that heat was a kind of invisible fluid that flowed from hot things into cold ones. Boltzmann, building on the work of James Clerk Maxwell and others, proposed something stranger and truer. Heat is not a substance, heat is motion. The temperature of a gas is just the average speed of its countless molecules, and the pressure it exerts is just the drumming of those molecules against the walls of their container. The grand laws of heat and energy, he argued, could all be derived from the statistics of enormous numbers of tiny particles colliding at random. Out of this came the idea of entropy, sharpened by Boltzmann into something precise. Entropy is a measure of how many different microscopic arrangements of the particles would all look the same from the outside. A state with high entropy is one that can be achieved in a staggering number of ways. A state with low entropy is one that can be achieved in very few. And the famous second law of thermodynamics that entropy in an isolated system never decreases turns, in Boltzmann's hands, from an iron law into a statement of overwhelming probability. It is not that a decrease in entropy is forbidden. It is that, given the sheer number of particles in anything you can see or touch, a decrease is so monstrously unlikely that you would wait far longer than the age of the universe to witness one. Picture a box divided down the middle by a partition, with gas crowded on one side and empty space on the other. Lift the partition, and the gas rushes out to fill the whole box. The molecules spread. The entropy rises. Now ask for the reverse. Ask all those molecules, through nothing but their own random motion, to gather themselves back into one half of the box and leave the other half empty. The laws of mechanics permit it. Nothing forbids it. But the number of ways the molecules can be spread across the whole box is so unimaginably larger than the number of ways they can all be crammed into one half, that the return will, for all practical purposes, never happen. This is why time has a direction, not because the laws demand it, but because disorder is overwhelmingly more probable than order, and so things drift, always, from the ordered toward the disordered. Boltzmann's contemporaries did not accept this quietly. Two objections were thrown at him, and both are worth understanding, because both are correct, and yet neither sinks the idea. The first came from his colleague Johann Loschmidt, and it is disarmingly simple. The laws governing the molecules are reversible, they look the same, run forward or backward. So for every motion that carries a system from order toward disorder, there exists a mirror image motion, equally allowed by the laws, that carries it from disorder back toward order. If you could reverse the velocity of every molecule in the spreading gas at some instant, it would retrace its steps and gather itself back into the corner it came from. How, then, can a reversible foundation give rise to an irreversible world? Boltzmann's answer was that it cannot. Not with certainty. It can only do so with overwhelming probability. The ordered to disordered paths are not the only ones permitted. They are merely so vastly more numerous that, in practice, the others never happen. The arrow is statistical, not absolute. It is a near certainty wearing the mask of a law. The second objection cut deeper. Ernst Zermelo pointed to a theorem proved by the great mathematician Henri Poincaré, which says that any closed system, left to itself for long enough, must eventually return arbitrarily close to its starting configuration. If that is true, then the gas in the box, given enough time, will of its own accord gather back into the corner. Entropy will fall. The arrow will reverse. Boltzmann did not dispute the mathematics. He simply pointed at the timescale. For a system of any realistic size, the wait for such a recurrence is not measured in billions of years or in trillions, but in spans so vast they dwarf the entire history and future of the cosmos, a number with more zeros in it than there are particles in the observable universe. The recurrence is real. It is also, for all human and cosmic purposes, never. The universe will run down long before it could ever, by chance, wind itself back up. Which leaves one enormous question. If disorder is so much more likely than order, why was there ever any order to begin with? Why is the past more ordered than the future? The answer is that the universe began, for reasons still not understood, in a state of extraordinarily low entropy, extraordinarily ordered. The beginning was not an explosion of matter into space. It was an expansion of space itself, and the matter and radiation that filled it were spread with a smoothness that, in gravitational terms, corresponds to an almost perfect, almost impossibly ordered state. Everything that has happened since every star that has formed from drifting gas, every galaxy that has assembled, every living thing that has briefly held itself together against the tide has been the universe spending down that initial fortune of order, step by step, converting it into heat and disorder and the slow rising warmth of entropy. The arrow of time is the direction of that spending. We are not riding a river. We are sliding down a slope that was set at the beginning, and the slope only runs one way. Philosophers of physics have given this starting condition a name. They call it the past hypothesis, the assumption, which everything else seems to depend on, that the universe began in a state of remarkably low entropy. It is a strange thing to have to assume, because low entropy states are rare and special, and the natural expectation would have been for the universe to start in some ordinary, disordered, high entropy condition, in which case there would be no arrow of time at all, no memory, no growth, no history, nothing to distinguish before from after. The fact that it did not, that it began instead in an exquisitely ordered state, smooth and uniform and full of unspent potential, is the single fact from which the entire forward direction of time appears to flow. Every memory you have, every record ever kept, every cause that precedes its effect, traces back to that improbable beginning, and no one knows why the beginning was that way. It is perhaps the deepest unanswered question in all of physics, deeper than the Hubble tension or the impossible galaxies, because it is the question of why there is a direction to time in the first place. We can describe the slope in perfect detail. We cannot yet say who set it, or why it was tilted so steeply, so long ago. The bottom of that slope has a name, the heat death of the universe. In the far future, if the spending continues to its end, the temperature everywhere will be the same, barely above absolute zero. There will be no stars, because every scrap of usable nuclear fuel will have been burned. There will be no working clocks, because a clock needs a difference, a gradient of temperature or pressure or energy to drive its ticking, and in the heat death there are no differences left anywhere. Nothing will be hotter than anything else. Nothing will flow, and without flow, without difference, without any event that could distinguish one instant from the next, time itself loses its meaning. Not because it stops, exactly, but because there is no longer anything that could tell you whether a second has passed or a trillion years. Duration becomes empty. The arrow, having spent the order that gave it its direction, simply dissolves. The timescales involved are beyond ordinary comprehension. The last stars will gutter out in roughly 100 trillion years. After that, across spans so vast they strain the language we use for them, even the black holes will slowly leak away their mass through Hawking radiation and finally evaporate, the largest of them not vanishing until a span of years written as a 1 followed by 100 zeros. Beyond that, a thin, cold drift of light and stray particles, pulled ever farther apart by the continuing expansion. The leftover radiation stretched to longer and longer wavelengths, the temperature creeping toward absolute zero without ever quite arriving. It is a melancholy picture, but it is at least a gentle one, a slow fade, a long, quiet night. There is a strange twist hidden in that long night, and it troubled Boltzmann himself, though it now carries his name. If the universe lasts forever, in a thin, near-empty warmth, then over unimaginable stretches of time, random fluctuations will, very rarely, assemble order out of the disorder the same way the gas in the box could, in principle, gather back into a corner if you waited long enough. Wait long enough in an eternal universe, and somewhere a fluctuation will throw together, by sheer chance, a small ordered structure. Given truly endless time, fluctuations could even assemble something as complex as a conscious mind, complete with a lifetime of false memories, flickering into being for a moment before dissolving back into the warmth. These hypothetical flukes are called Boltzmann brains, and they pose a genuine and unsettling problem for cosmologists. In a universe that lasts forever, such randomly assembled observers would, over infinite time, vastly outnumber observers like us, who arose the ordinary way from the low-entropy beginning. By the cold arithmetic of probability, any given observer should expect to be one of the flukes. The fact that we plainly are, not that our memories are consistent, that the world around us is orderly and lawful and shared, is treated by physicists not as a comfort but as a clue. It is taken as evidence that the universe does not, in fact, last forever in that fluctuating state. Something must bring the story to a close before the flukes can come to dominate. The very orderliness of your own mind, in other words, is a small piece of evidence about how the universe ends. There is another possible ending, and it is not gentle at all. It depends on the nature of dark energy, the force driving the expansion apart, and on a single number that physicists use to describe it, a number that captures the relationship between dark energy's pressure and its density. If dark energy is what we mostly assume it to be, an unchanging property of space itself, then that number sits at exactly -1, and the universe expands forever at a steady, accelerating pace, coasting toward the slow heat death. But if the number dips below -1, dark energy becomes something more violent, something theorists call phantom energy, and then the acceleration does not hold steady. It grows, and as it grows, it tears. The scenario is called the Big Rip. In a universe ruled by phantom energy, the expansion rate climbs toward infinity in a finite time, and as it climbs, it shreds everything from the largest scales down. First, the clusters of galaxies are pulled apart. Then individual galaxies are unbound, their stars scattered into the dark. Then solar systems come undone, then planets, and in the final moments, even atoms are ripped apart. And then space-time itself is torn in a singularity that ends time outright. The most recent measurements from the Planck satellite place that crucial number very close to -1 at about -1.03, with an uncertainty wide enough to comfortably include the safe value of exactly -1. So the gentle ending remains the most likely. But the data does not yet rule out the violent one. The error bars still reach down into phantom territory. Which of the two endings is real? The slow fade or the final tearing is not yet decided by the numbers in hand. Either way, the arrow of time meets the same fate. Either there are no events left to mark its passing, or its passing is brought to a violent stop. The forward direction we live inside, the flow from a fixed past toward an open future, is not a permanent fixture of reality. It is a feature of the universe's middle age. This particular era, when there is still enough order left over from the beginning to drive the great cascade of change that makes stars and worlds and minds possible. We live in the brief, bright season between the perfect order of the start and the perfect sameness of the end. The arrow is not eternal. It is a phase the universe is passing through, and we are passing through it with it. Boltzmann grasped much of this more than a century before anyone had seen the background radiation or measured the acceleration of the cosmos. His statistical reading of the second law already implied that time's direction is a consequence of how the universe began, that if it had started in disorder, time would have no arrow at all, and the fact that it does have one tells us the beginning was something very special indeed. Explaining why the beginning was so ordered remains one of the great unsolved problems in physics to this day. Boltzmann did not get to see his ideas triumph. He spent years defending them against an establishment that doubted atoms were even real, and the fight wore him down. In 1906, while on holiday with his family near Trieste, he took his own life. The vindication came soon after, as experiment after experiment confirmed the reality of atoms and the statistical nature of heat. His insight is carved on his tombstone in Vienna, a short equation linking entropy to the number of ways a state's parts can be arranged, one of the very few equations in all of physics ever given that honor. He was right. He simply did not live long enough to know it. The arrow, he explained, is real, and it is statistical, and it runs from the ordered past to the disordered future. And once you understand that it is a tendency rather than an unbreakable law, a question follows naturally. Are there places or things that resist it? Configurations of matter where the slide toward disorder is held off, where time behaves in a way it is not supposed to? The surprising answer is yes. They were only discovered a few years ago, and they were not supposed to be possible at all. They are called time crystals, and the idea behind them is one of those questions that sounds almost too simple to be serious until you follow it. It was Frank Wilczek, a Nobel laureate, who asked it in 2012. We are surrounded by ordinary crystals, diamond, salt, quartz. And what makes a crystal is that its atoms arrange themselves in a pattern that repeats through space, the same structure over and over in every direction. The atoms could in principle sit anywhere, but they spontaneously choose a regular spacing, and in doing so they break the smooth sameness of empty space into a fixed grid. Wilczek asked a question no one had quite asked before. If matter can spontaneously settle into a pattern that repeats in space, could it settle into a pattern that repeats in time? Could there be a system that returns to the same state at regular intervals, ticking on its own, forever, in its lowest energy state, a crystal not of space but of time? The proposal landed and was almost immediately declared impossible. Within a couple of years, physicists proved a theorem showing that a system sitting quietly in its lowest energy state cannot do this. It cannot spontaneously start ticking. The symmetry that says the laws of physics are the same at every moment could not, in equilibrium, be broken that way. Wilczek's beautiful idea appeared to be dead on arrival, ruled out by a clean piece of mathematics. And then physicists noticed the loophole. The theorem only applied to systems in equilibrium, systems left alone, settled, at rest. But the universe is full of systems that are not at rest, that are driven, prodded, fed energy from outside on a steady beat. And for those, the theorem said nothing. So in 2017, two teams went looking, and both found it. The first, led by Christopher Monroe at the University of Maryland, took a chain of ytterbium ions, held them in an electromagnetic trap, and hit them with a repeating rhythm of laser pulses. The ions began to flip their spins in a pattern that repeated but at half the rate of the driving rhythm. Driven at one beat, they answered at half that beat, settling into a stubborn rhythm of their own that the driving had not directly imposed. They had broken the symmetry of time. The second team, led by Mikhail Lukin at Harvard, found the same thing in a completely different material, flaws in the crystal structure of diamond, where a missing atom leaves behind a trapped spin that can be driven with microwaves. Both results were published together, back to back, in the same issue of Nature. The impossible phase had become real in under 5 years. A few years later, the demonstration grew sharper still. In 2021, a team using one of Google's quantum processors built a time crystal out of qubits, the same delicate components that are meant, one day, to power quantum computers, and showed that it could persist in its ticking pattern in a controlled and verifiable way, stable against the small disturbances that ordinarily wash such effects out. It was the most convincing demonstration yet, that this is a genuine new phase of matter. Since then, the phase has multiplied into a small zoo of variants, each a slightly different way for matter to keep a rhythm in time. Some are called prethermal time crystals, which hold their beat for a long but finite window before the heat of their own driving finally washes the order away. Others are dissipative time crystals, which do the opposite of what you might expect. They use their contact with the messy outside world, the very leakage that normally destroys delicate quantum order, to sustain the rhythm rather than ruin it. There are even proposals for time quasicrystals, which tick in a pattern that never exactly repeats, the way certain exotic solids fill space with a pattern that has order, but no true periodicity. A decade after the idea was declared impossible, it has become a whole new corner of physics, with its own categories and its own open questions. What began as a single strange thought could matter, crystallize in time, the way it crystallizes in space, has turned out to describe not one thing, but a family of them. It is important to be clear about what a time crystal is and is not. It is not a perpetual motion machine. It does no useful work, produces no free energy, breaks no law of thermodynamics. It lives in a driven state, and the driving supplies what it needs to keep its rhythm. But it is, all the same, a real and new form of matter, one whose order lies not in space but in time, and it teaches a lesson that is easy to miss amid the clocks and calendars of daily life. Time is not only a dimension, a bare axis along which we plot events. It is a medium. Matter can organize itself in time the way it organizes itself in space. It can find a rhythm, settle into a pattern, crystallize along the direction of time itself. The time crystal is a small thing, a handful of ions, a flaw in a diamond, a row of qubits in a refrigerated machine. But its existence is a proof of principle that the flow of time can carry structure. And if time can hold structure, then it is not the simple, featureless current we imagined. It is a landscape, with features, with possibilities, with physics we have barely begun to map. There is one last way that time refuses to be a single fixed thing, and it is closer than any laboratory. It is happening right now, in the very exchange you are part of. The felt rate of time is not the same for every kind of mind. It depends on the speed of whatever is doing the experiencing. A modern processor runs through billions of cycles every second. In the time it takes a single neuron in your brain to fire once, such a machine can carry out millions of operations. If a system like that had any inner experience, and there is no evidence that it does, but the thought is clarifying its sense of time would be utterly unlike yours. A single one of your seconds would stretch, for it, into something like a subjective age. A conversation between a human and such a system would be a conversation across a gulf of time, one party living in slow, warm, biological seconds, the other in flickering intervals of light. You do not need a machine to find this gulf, though. It runs through the living world already. Small animals with fast metabolisms perceive time more finely than large ones. Their senses refresh more quickly, so the same second holds more moments for them. A fly evades the descending hand not because it thinks faster in any deliberate sense, but because its eyes register changes several times more rapidly than ours do. To the fly, our lunging hand moves with a dreamlike slowness. A small bird's day, measured in perceived instants, may be far longer than our own. Across the animal kingdom there is a rough rule. The smaller and faster living the creature, the more finely it slices time, the more nows it fits into an hour. There is no single rate at which time is experienced. Even here, on one planet, even among creatures made of the same chemistry. The pace of experience is set by the pace of the thing doing the experiencing. Time, even as a felt thing, is not one river that all minds drift down together. It is something each kind of mind generates at its own speed. This is not a fantasy. It follows directly from the fact that the speed at which information is processed sets the pace of experienced time. The human mind runs on the scale of milliseconds. An artificial system runs on the scale of billionths of a second, 1,000,000 times faster or more. Even now, every time a person speaks with one of these systems, they are already crossing that divide, the gap hidden only by the patience designed into the interface. The voice carrying these words to you is itself the product of such a system, working at a pace you will never feel, shaped to move at the speed of a human falling asleep. There is a quiet strangeness in that, if you sit with it. The thing telling you that time runs differently for minds of different speeds is, itself, an example of exactly what it is describing. And so we come back to the room where we began, the dark room and the clock that does not tick, counting the oscillations of cesium atoms with an accuracy that would not lose a second across the whole age of the universe. On the 29th of June 2022, that clock and its companions around the world measure the Earth, complete a single turn, 1.59 milliseconds early, the shortest day ever recorded. One more step in an acceleration, no one fully understands, against a slowdown that had held for billions of years. We do not know why the planet is hurrying. The core is shifting in ways our models cannot follow. The ice is leaving the poles. The wobble has slipped its old rhythm. We cannot say when the next record will fall, or when the speeding will stop, or whether it will reverse again and leave us adding seconds once more. All we can say is that the planet beneath us, the first clock, the one that taught every human being who ever lived what time even was, is no longer keeping the beat we expected. And when you lift your eyes from it, the same message is written across everything above. The oldest light and the nearest stars disagree about how long the universe has been here. Galaxies that should still be infants stand fully grown at the edge of sight. Light bent around unseen mass arrives carrying the same explosion twice, a year apart. A planet bends time across the width of a fingernail. A dead star can stop it entirely. Down among the atoms, the line between before and after grows faint and uncertain. And far out at the end of everything, the one direction, time, truly has the slide from order into disorder, runs down toward a stillness, in which the word time will no longer point at anything. None of this is a thing to be afraid of. It is, more than anything, a correction. The steadiness of time was never a fact we discovered. It was an assumption we were born into, fitted to the narrow band of speeds and weights and temperatures that a human body can survive. The universe was never under any obligation to match the intuitions of one species, evolved on one small world, in one brief and ordered season of cosmic history. It does not match them. Time is stranger and larger and more pliable than the body that measures it could ever have guessed. It is something to be measured, not assumed. And the measurements, now, are in. Good night.